Alright, so in our last video we started talking about using Riemann sums to approximate the area under a curve, and we did two examples. We're moving into example 3, where we're going to find the area under the function y plus y equals, or f of x equals 3 plus 2x minus x squared on the interval 0 to 3, using midpoints this time, and 6 sub-intervals, 6 rectangles. So let's start by finding our delta x, the amount all of our values are going to go up by, the width, in a way, of our rectangles. So we're going to take 3 minus 0 and divide that by 6. So we're going to get 3/6, or a half. So at every half, that's going to be the width of our rectangle. So between each half is where we're going to put that point. So we're going to start by, when we're doing midpoints, it doesn't really matter if you start from the left or the right, but we're going to go between 0 and half, and we're going to draw an imaginary line up, and we're going to put a point there. Then we're going to draw a line over to 0 and a line over to the half and make our first rectangle. That point is going to be the one we're using in our approximation. Then we're just going to keep repeating that process until we finish putting in our 6 rectangles. Alright, so now we can start finding this. Since this is a midpoint approximation, we're going to write MP for midpoint, and we broke it into 6 intervals. So we're going to take our delta x, and we're going to multiply that by f of 0.25, that's halfway between 0 and a half, plus f of 0.75 plus f of 1.25 plus f of 1.75 plus f of 2.25 and f of 2.75. We can plug those values into the function, get the actual y values, and then we can replace our delta x. So we're going to have 1/2 times 3.4375 plus 3.9375 plus 3.9375 again, plus 3.4375 plus 2.4375 plus 0.9375. And if we add all of those, we're going to get 1/2 times 18.125. And then if we do the multiplication, we're going to find that the area is about 9.0625 square units underneath the curve between the endpoints, between 0 and 3. Now, something to take note of as we work through this process. Some things should maybe start becoming apparent. Drawing the function is not always actually necessary. The more rectangles that we create, the more work we end up doing, and it's just a lot of arithmetic, a lot of multiplying and a lot of adding. And in each case, the base is the same, which allows us to factor it out. And then the only difference between the left endpoint and right end sums is that the first and the last height. And we start on left end sums drawing from the left end, and from right end sums we start drawing from the right end. So what we're going to do is we're going to try to come up with a hypothesis here in example 4 for when you will get an underestimation or an overestimation depending on the type of sum we use. So we've got a table here, f of x. If f of x is increasing and we've got a function that's concave up, I'm just going to give you this information. If it's a left-hand sum, what's going to happen is we are going to be underestimating in that case. If it's a right-hand sum, we're going to overestimate. So we'll never be able to say under and under or over and over. In all 4 of these cases, or really all 8 of these cases, 4 little subgroups, we're going to have an under and an over. So if we're increasing and we're concave down, taking a left-hand sum, we're going to end up underestimating. And a right-hand sum, we're going to end up overestimating. Now, if we're concave up and decreasing, we're going to flip these. So a left-hand sum, we're going to overestimate, and a right-hand, we're going to under. And then it's the same with concave down. Left-hand sum, we're going to have an overestimation. Right-hand, we're going to underestimate. And that's fine. Remember, we're just estimating the area. All right, moving on to our final example, example 5. This table below represents the velocity, v of t, in feet per second of a car traveling on a straight road over a 50-second time interval. We want to estimate the distance the car traveled over the interval using right-hand sums and left-hand sums, along with 2 different approximation techniques. We can use a midpoint and a trapezoid rule. So what we're going to do first is estimate the total distance traveled by the car by using a left-hand sum method with 5 partitions of equal length. And we're going to show the setup and draw the rectangles on graph 1 here. And we're going to use blue to do that. You can use whatever color you want in your notes. So since we see that our endpoints are 0 and 50, we want this to be in 5 partitions, so that means our delta x is going to be 50 minus 0, so 50 over 5, so our delta x is going to be 10. And we're doing left-hand partitions, left-hand rectangles. So with our first rectangle, we aren't really drawing much. We've just got a little guy right there. Our second rectangle, we draw straight up from our first one and then over once we touch the graph. And then we continue that until we've got our 5 rectangles. And it is okay if we cross the function a couple times. So we've got our 1, 2, 3, 4, 5 rectangles here in blue. Now we're going to show our work for finding this. So we're going to take our delta x, our left hand, in 5 partitions. We take our delta x, and we're going to take 5 values we're going to take at 0, at 10, at 20, 30, and 40. So we're going to take delta x times 0 plus 20 plus 52. We're taking the value at the function. Plus 80 plus 77. It's kind of nice when they have this table here for us. So we know delta x is 10. So we're going to add all those numbers and then multiply them by 10. So I'm going to just replace delta x with 10, and then I'm going to add the numbers. If we add them, we're going to get 229. It's going to be 10 times 299 feet for the total distance that this car traveled. If we multiply, we're going to get 2,290 feet as an estimation or an approximation. Now for part B, we're going to use a right-hand sum. Again, 5 rectangles, but we're going to draw them in red. So it might be helpful if you do have 2 different colors to do this, because now I'm going to take my red pen and I'm going to use the same graph, and I'm going to create from the right hand side rectangles. So with the blue rectangles, we had a bit of an underestimation. I'm just looking at the picture and I'm seeing that there's a lot of those red rectangles that are outside or above the curve. So we might get an overestimation here. So now we're going to still take our delta x with our right hand estimation in 5 rectangles. So delta x we know is 10. We're going to look at from the right. So we've got here at the 50. We've also got the 40, 30, 20, and 10 values. We're ignoring this 0 this time. So we're going to have 10 times 20 plus 52 plus 80 plus 77 plus 74. Which is going to give us 10 times 303 feet, which is about it is 3,030 feet. So let's continue. So now we're going to use the midpoint sum with 5 rectangles. And the first rectangle, it's already shown in graph 2. So we're just going to complete the setup. And really, as far as what we need to know, we're not going to do this trapezoidal sum deal, but we're going to finish putting in our rectangles for this midpoint sum. So let's continue doing that. We're going to go halfway between 10 and 20. Halfway between 20 and 30. Halfway between 30 and 40. And halfway between 40 and 50. So this is going to be the last part of our example. We're not going to, in our note packet, fill in D and E. Trapezoidal, using the trapezoidal rule to do this, we're getting into like Calc 2 topics there. So we're just going to focus on left-hand sums, right-hand sums, and midpoint sums. So in here, we're still going to use a lot of what we were doing before. We're going to take our delta x, and this time we've got values at 5, x values at 5, 15, 25, 35, and 45. So we're going to multiply delta x by the sum of 14 plus 28 plus 70 plus 86 plus 70 again. Delta x is still 10, so we're going to go 10 times, and if we add all of that up, we're going to get 268. So 10 times 268 feet. So we're going to see that the car has traveled 2,680 feet. And that's actually going to wrap up our lesson on area under a curve.